Okay, last time we just uh talk about the injective functions. Uh, injective functions is also called one-to-one functions. That means um, you only uh have one first element for each second coordinate of the ordered pairs. So that means each element in the domain maps to a different element in the codomain. So that's called one-to-one. And we know we can determine whether a relation is a function graphically by a vertical line test, and we can determine a one-to-one function by horizontal line test. Just like the graph in here, the left hand side is not a function, it fails the vertical line test. But if you look at the right hand side curve and you try to define a function based on the curve from R to R, does it give us a function? Remember, it does pass the vertical line test. Any vertical line crosses the curve at most one point, but if you define from R to R, that means the domain is all real numbers. So then you should map the next x value to some real number. Okay, in other words, the curve should be including both positive and negative x values. That's the definition of function. For each element in the domain, you map only one element in the codomain. So you need to map negative x values into some real number or real numbers. But in here, the curve only includes the values of non-negative x. So the curve on the left-hand side of the plane is missing, so you cannot have a function value for negative x values. The graph doesn't define such a correspondence. So this is not a function from R to R. Okay. I think we talked about that before, but just make sure, it's not just good enough to pass the vertical line test. You still need to check the domain and the codomain to determine whether it's a function or not, because the function includes the domain, the codomain, and the root. All right. So it's not defined every day, in other words. Okay. So some vertical lines do not hit the curve. There are holes for all negative values of x. Okay. So just remind you that any function f from A to B satisfies two basic properties based on our discussion. The vertical line test for each point, there is at most one point. All right. So that's the vertical line test. And no holes in the domain. For each input, there is at least one output. Okay. You need to define a function in the whole domain, basically. And graphically, there should be no holes in the domain. All right. So so that's the function. Now, if you reverse the rows of domain and codomain, then as we did previously last time, then we turn the vertical line test into horizontal line test, and then we use that to determine whether a function is one-to-one or not, right? A horizontal line test tells you whether a function is one-to-one or not. So when we study surjective functions, we also can think of the same operation or start the same reversal, namely just change the null holes in the domain rule, change to null holes in the codomain. So basically what it means is for a surjective function, there should be null holes in the codomain. That means all the elements in the codomain need to be in one of the ordered pairs of the function. Okay. So here comes the formal definition of surjective functions. It says a function f from A to B is surjective if every element of B occurs at least once as the image under F of some element A in the set A, the domain. So in symbolic logic, we write for any arbitrary element in the codomain, we say this B. There exists some element A in the domain such that f of A equal to B. Okay, so in other words, the function is defined for each element in the codomain. So we say that function is surjective, or sometimes we call it onto. All right, so that means the function maps onto all elements of the codomain. So there should be no element left in the codomain not in all the pairs of the function. So so in other words, for each element B in the codomain, it is a second coordinate of at least one ordered pair in F. So it could be the second coordinate of one or two or three or more, but it has to be in at least one of the ordered pairs in F. All right. So let's just look at a simple example. Suppose we have function f defined from A to B, where the set A is the set of four numbers, 1, 2, 3, and 4, and the set B is three numbers, the set of 1, 2, and 3. So if you define the function f by this rule, okay, remember a function is a set of ordered pairs. So the pair of 1, 2, the pair of 2, 2, the pair of 3, 3, the pair of 4, 1. Okay, so if you look at the second coordinate for each order pair, we have 1, 2, and 3. So all of the elements in set B are in at least one order pair in the function. Okay, at least one. Actually, the number of 2 in set B appears twice as the second coordinate in all of the pairs of F. But that's perfectly fine. So this function is surjective. All right. And you can easily visualize the function by drawing the diagram and the arrows. So there are four elements, four numbers in set A, 1, 2, 3, and 4. And three numbers in set B, 1, 2, and 3. And then you can draw an arrow to indicate each of the pair. So 1 and 2, 2 and 2, 3 goes to 3, and 4 goes to 1. Okay, so all of the elements numbers in set B have at least one incoming arrow. Incoming arrows. Okay. So there is always at least one arrow pointing at any element of B. All right. Be straight. Okay. Let's look at some more examples. So suppose we define a function f from R to R by the rule of f of x equal to 2x plus 1. And if you graph the function, you will easily see that each horizontal line crosses the graph. So the function is on 2. So there's no holes in the codomain. In other words, whenever you draw a horizontal line anywhere, you will cross the graph. Okay. So it means for any real numbers, either positive or negative or 0 of y, you can always find the x value pairs with it, right? So that's if you think about the horizontal line. Okay, so how do you prove it? Actually, if you pick up any real number, say B from the codomain R, so that B be any real numbers, and if we let A equals B minus 1 over 2, then we can see that f of A equals B. Well, first, B is a real number, so B minus 1 over 2 is also a real number. So, so this number A is in the domain, all right? And if you evaluate the f of A or f of B minus 1 over 2, since that is A, then you just plug in A for x in f, which is B minus 1 over 2, so 2 times B minus 1 over 2 plus 1, so we get B minus 1 if you cancel 2 in the first term, and then you add 1, so you get B. So f of A equals B. So for any real number B, you can always find a real number A, so that f of A equals B. So that means f is surjective. All right. So and that's how you prove it. So you need to find the value A so that it satisfies f of A equals B, but also you need to make sure this A is in the domain. All right. So there are two parts actually. So that's a easy example. And the other question is, how do you find the value of A in the order pair of B in the function? And we didn't do it in the previous example. Now let's just show how we obtained this A, value of A. And that's pretty easy. If you set fx equal to b and then solve for x, that will give you A, right? Because that's what you want. You want the f of A equal to b. So that means b equals 2a plus 1. And you solve for A easily by subtracting 1 divided by 2. So A equals b minus 1 over 2. All right. Let's look at more examples. Suppose we define a function from R to R by f of x equal to x squared. So we want to know whether this function is onto or surjective. In other words, that this function passed the null holes in the codomain. The answer is not. We know this is a parabola passing through the origin, but the whole curve is on the upper half plane and the origin. So if you draw a horizontal line below the x-axis, and then there's no intersection between the line and the curve. So there are some holes in the codomain, right? So the codomain is all real numbers R. So if you pick up a negative value for the in the codomain for y, that means you draw a horizontal line below the x-axis. You do not cross the curve at any point. So it does not pass the low holes in the codomain test. All negative values are missed. Okay. Or in the codomain, all the negative values do not have a pre-image, do not have a x value paired with it. This is very easy to prove. So, for example, if you let b equal to -1, then you want to find some real number a in the domains such that a squared is equal to -1. And that's not possible, Any real number you square, you cannot get a negative number. So that means -1 does not have a pre-image to pair with it. That's because we define the function from R to R. The codomain is R. Okay, so this is not the surjective. It is a function, but it is not the surjective. All right. Now, if you change the function from R to non-negative numbers, okay, from 0 to infinity including 0, by the same rule, f(x) equals x squared, then it is surjective function. Because this time, when you choose any value in the codomain between 0 and infinity, you can always find the square root for a non-negative number. Okay. So for example, pick up any value b from 0 to infinity and let a equal square root of b, then obviously a is real, actually is either positive or 0 as a real number, obviously. And if you evaluate a, you got f of square root of b, which is square root of b squared, which is b. So for any element or number in the codomain, you can always find at least one element in the domain A that pairs with B. Okay. So that means this function is onto or is surjective. And you just pick one of those. Actually, it has two numbers paired with it for each B. It has two numbers in this first coordinate of all the pairs, both positive and negative, for any positive number B. And for 0, it only has one number to pair with it, which is 0. But for any positive number in the codomain, you can always find the two numbers in domain paired with it. So that is a surjective function. Okay. Let's look at one more example we did before. This rational function defined from r minus the set 2 to the set of r minus set 1. So what it means is this function is defined from all real numbers except 2 to all real numbers except 1. Okay. And the function is f equals x minus 1 over x2. And if you draw a graph of this function, it includes two branches. One on the upper right, above horizontal line, one branch the lower left, below the horizontal line 1, and on the left vertical line 2. Okay. And the first branch is also on the right side of x equal to 2, and above the horizontal line y equal to 1. So you can easily see that it is surjective because for any real number except 1, if you draw horizontal line, except for 1, you know, you can always find the intersection of the curve with the horizontal line. So it is indeed subjective. This function only has one hole in the codomain. Okay. If our codomain is R, but obviously our codomain is R minus the set 1. So in other places except 1, it does not have a hole in the codomain. Okay, in the function defined here. So we just limit the codomain to R minus set 1 and remove this hole. Okay. And then how do we prove this surjective function? Once again, you just pick up any value b from the codomain, which is R minus set 1, and you let a equals 2b minus 1 over b minus 1, and then and you should be able to show that the f of a equals b, and that's pretty straight. But also, the other thing you need to do is you want to show this a is one element in the domain, which is R minus set 2. Okay, so there are two parts for the proof. So we need to show this a is not equal to 2, basically. Well, so we know a is a real number, obviously, as b is not equal to 1. So then what if we set this a equal to 2? Then you can easily find out you're going to get the -1 equal to -2 if you multiply b minus 1 on both sides and simplify a little bit. So we got 2b minus 1 equals 2 times b minus 1. Okay. And distribute 2 on the right side, you got 2b minus 2, and you cancel 2b on both sides, you get -1 equal to -2. So that's a contradiction that cannot happen. So that means a cannot be equal to 2. Okay. So in other words, for any number B in the codomain, we will not end up with A equal to 2. Okay, that will not happen. All right, so that means A is in the domain of R minus set 2. Okay. For any number B in the codomain, this value A defined here is in the domain. And then we need to show that f of A equals B. Okay, so A is in the domain, which is R minus set 2. So remember the definition of the function is x minus 1 over x minus 2. So f of A equals A minus 1 over A minus 2. And A is just you know 2b minus 1 over b minus 1. Okay, so you just simplify this complex fraction. If you remember, there are two different ways to do it. And the easy way to do it is just multiply the least common denominator of all the fractions on top and at bottom. And in this case, it's b minus 1. So you just multiply by b minus 1 both on the top and at the bottom. So, and you just distribute b minus 1 on each term, both on the top and on the left. Okay, so in the first term of the numerator, b minus 1 and b minus 1 cancel. So you end up with 2b minus 1 and minus 1 times b minus 1, which is b minus 1. At the bottom, you just cancel b minus 1 with b minus 1, I get 2b minus 1 in the first term, and then minus 2 times b minus 1 if you distribute b minus 1. And so you did on the top. Okay, so and then you just simplify the top and the bottom separately. So the negative sign becomes positive when you distribute it to -1. So we got 2b minus 1 minus b plus 1 on the top. -1, +1 cancels, and 2b minus b just b. At the bottom, if you distribute -2 to b minus 1, you get -2b plus 2, and 2b and -2b cancel. -1 plus 2, which is 1. So we got b over 1, which is b. So f of A equals b. So so that means for any number in the codomain, you can always find a number in the domain paired with it. So that's a surjective function. So once again, this shows how we find this A value from B. Okay, so how did you find the A equals 2b minus 1 over b minus 1 given any b in the codomain? Okay, so what you do is just solve the equation of b equals a minus 1 over a minus 2. So, b is an arbitrary number in the codomain. So that's the f of x or f of a. And you want this f of a equal to b. You want to find such a, so that f equal to b. So, and then you just set the a minus 1 over a minus 2 equal to b and solve for a. Okay, so that's easy to solve, as we know. We got a fraction on the left. So why don't we just multiply the least common denominator, which is a minus 2 on both sides with the equation. So we got the a minus 1 on the left because a minus 2 just cancels. And on the right side, we got b times a minus 2. And you can distribute the b on the right side. You get b times a minus 2b, but b times a just a times b or ab. And then we want to solve for a from this equation. So, given b, solve a, right? So what you do, just separate the terms with a on one side and the other terms on the other side. So If we move negative 2b to the left, it becomes positive 2b, and you also move a to the right, it becomes negative a. So we got 2b minus 1 equals ab minus a. And then you can factor a on the right side, you get a times b minus 1, and then you divide by b minus 1 both sides, you get a equals 2b minus 1 over b minus 1. So that's pretty straight. So that's how we found the a value corresponding to the b in the codomain. By the way, these steps are not necessarily written in the proof. You know, in the example, we didn't actually write these steps, and actually in another example we did before, we also didn't show all these steps. You know, when we do the you know, the example 17 in here. Okay. So that's another example of a surjective function. Okay, let's just look at one more example. This time we're talking about the P of S. You know, if you still remember what it means, you know, given a set S, the definition of capital P of S, discrete P of S is all the what subsets of S, including S itself. So this is called the discrete P of S. And this time we will let A equals discrete P of S minus the empty set. Okay, all right. So then we define a function from A to S by this rule, by letting f of x, where x is one of those elements in A, by letting the value of the function be the least element of x. So x is a subset of S, and you just pick up the least element in this subset. Okay, so you have a bunch of subsets for S, and we're not talking about the empty set, so that's why we need to exclude the empty set from all the subsets of S. We know empty set is always a subset of any set, so we need to take it off. Then all the elements in the domain, which is A, will include at least one number. It will not be empty, so it will, you know, it is a subset of S, and it is not the empty set, so it has to include at least one number. Okay, so then we can talk about the least element, or the smallest number in this set. So just make sure it's defined, it's well defined. You can always find such a element. Okay. So it's easy to see that f is function from A to S. For example, f of the set 3, 4, 5 is equal to 3, the least element. F of the set of 2, 4 equals 2, the least element. Okay. So so you can define different types of functions, you know. So this function is defined from a set to a number. Okay. So the argument of the function, in other words, is a subset of S. All right. It is a function because given any non-empty subset of this S, you can always find at least an element. Okay. And only one list element, right? So it is a well-defined function. And then you can easily show that the function is also surjective. Okay, what it means is, given any number in S, okay, so this function is defined from A to S. So that means for any element in S, in the codomain S, which is 1, 2, 3, 5, 4, 5. So given any of those numbers, you can always find at least one subset of S so that the element of that subset is that number. And that's easy to show, okay? So just pick up any number B in this set S, and then you just let A equals the set of B. Okay, so that's just a set of one element or one number, the B itself. So that set A is a set, is element of capital A, because it is the subset. That's the set of element B is a subset of S, right? Because B is the element in S, all right? And it's not empty. So this is in the domain. So this A is in the domain. And then the least element of this set B is B itself. So then f of A equals f of set B, which is the element of this set, which is B. So f of A equals B. So for any B in this codomain S, you can always find at least one such A in the domain A. So such that f of A equals B. So this proves that f is surjective. And you can find other subsets in the domain A, also, so such that f of A equals B. But you only need to find one. So then it completes the proof. So this function is surjective. Okay, so let's just stop here, and we'll continue next time on Wednesday.